Imagine a celestial object, a cosmic entity unlike any we've ever observed. Picture it as the antithesis of a black hole where matter and energy erupt outwards. This is the concept of a white hole, predicted by Einstein's theory of general relativity. White holes are thought to be regions from which matter and energy spontaneously emerge. Unlike black holes which pull everything in, white holes repel matter. They are a fascinating enigma in the cosmos. Their existence remains theoretical, intriguing scientists and fueling our imaginations. White holes in theory possess properties like mass, charge, and angular momentum. These characteristics manifest in opposite ways. A black hole's mass contributes to its pull, while a white hole's mass might influence its repulsive force. The charge of a white hole could interact with electromagnetic fields. The angular momentum of a white hole relates to its rotation, influencing emitted matter and energy. These similarities and differences highlight the intriguing relationship between these two theoretical opposites. While black holes consume everything, white holes expel matter. Nothing can enter a white hole, just as nothing can escape a black hole. This fundamental difference lies at the heart of their contrasting natures. They are two sides of the same theoretical coin, representing opposing behaviors within spacetime. One devours, the other expels. One imprisons, the other liberates. Their opposing natures create a fascinating dynamic within cosmology. White holes, unlike their black hole counterparts, are hypothesized to exhibit a repulsive force. Instead of drawing matter inwards, they are thought to expel matter and energy outwards. This repulsion is a key characteristic that distinguishes them from black holes. Imagine a cosmic fountain, constantly spewing forth matter and energy into the universe. This outward flow is a defining feature of the theoretical white hole. The mechanism behind this repulsion is still a subject of speculation and ongoing research. Some theories suggest that the repulsive force might arise from the same principles that govern the immense gravity of black holes, but operating in reverse. Others propose that quantum effects near the singularity of a white hole could contribute to the outward pressure. The exact nature of this repulsive force remains a mystery, a puzzle that scientists are eager to solve. The repulsive force of a white hole is theorized to be so strong that nothing can penetrate it. Just as the event horizon of a black hole acts as a point of no return, the anti-horizon of a white hole would prevent anything from entering. Any matter or energy approaching a white hole would be deflected and pushed away by this powerful repulsive force. This impenetrable barrier further reinforces the contrasting nature of white holes and black holes. The relationship between black holes and white holes is deeply intertwined with the concept of spacetime. Einstein's theory of general relativity describes spacetime as a four-dimensional fabric that can be warped and distorted by massive objects. Black holes create deep wells in this fabric, while white holes are theorized to create the opposite peaks or fountains. This interconnectedness within the fabric of spacetime suggests a fundamental link between these two theoretical objects. Some theories propose that black holes and white holes could be connected through hypothetical tunnels in spacetime known as wormholes. A wormhole could potentially act as a bridge between a black hole and a white hole, allowing matter and energy to travel between different regions of the universe, or even different universes altogether. This concept, while highly speculative, offers a fascinating glimpse into the potential interconnectedness of the cosmos. Another perspective suggests that white holes could be the other end of black holes, representing the exit point for matter and energy that has fallen into a black hole. This idea implies that a black hole could act as a gateway to a white hole, transporting matter and energy across vast cosmic distances. This concept further strengthens the theoretical link between these two contrasting objects. Visualizing a white hole can be challenging, as they have never been directly observed. However, based on theoretical models, we can imagine them as intensely bright objects, radiating energy outwards. This brightness would result from the continuous expulsion of matter and energy from the white hole. Picture a cosmic beacon shining brightly against the backdrop of the universe. Unlike the dark, absorbing nature of black holes, white holes would be sources of intense light and radiation. This stark contrast in visual appearance further emphasizes their opposing natures. While black holes are regions of darkness and absorption, white holes would be regions of light and emission. Their contrasting appearances reflect their fundamental differences in behavior. The emitted matter and energy from a white hole would likely create a visually stunning display. We might imagine swirling clouds of gas and dust, illuminated by the intense radiation emanating from the white hole. This cosmic spectacle would be a testament to the immense power and energy associated with these theoretical objects. Section 5. Defining key terms: spacetime, singularity, and event horizon. Understanding the concept of white holes requires grasping a few key terms. Spacetime, as described by Einstein's theory of general relativity, is the four-dimensional fabric of the universe, encompassing both space and time. It is the stage upon which all cosmic events unfold. Massive objects warp and distort this fabric, creating the gravitational effects we observe. A singularity is a point of infinite density, theorized to exist at the center of both black holes and white holes. In a black hole, the singularity represents a point of infinite collapse, where matter is compressed to an infinitely small point. In a white hole, the singularity might represent the point of origin for the expelled matter and energy. This point of infinite density is a key feature of both objects. The event horizon of a black hole is the boundary beyond which nothing, not even light, can escape. It marks the point of no return for anything that crosses its threshold. White holes theoretically would have an anti-horizon, a boundary beyond which nothing can enter. These boundaries define the regions of influence for both black holes and white holes. Section 6. Theoretical formation of white holes. The formation of white holes remains a topic of ongoing theoretical research. One intriguing possibility suggests that white holes might arise from the quantum effects near the surface of a black hole. These quantum fluctuations could potentially halt the collapse of a black hole and slowly reverse the process, eventually leading to the expulsion of the original star matter. This scenario offers a potential pathway for the creation of a white hole. Another theory proposes that white holes could be formed through the decay of black holes. As black holes evaporate through Hawking radiation, they might eventually reach a point where they transition into white holes. This transition would mark a dramatic shift in the object's behavior, from absorption to expulsion. This scenario suggests a potential evolutionary link between black holes and white holes. Some scientists speculate that white holes could be created during the extremely high-energy conditions of the early universe. The rapid expansion and extreme densities present shortly after the Big Bang might have provided the ideal environment for the formation of these exotic objects. This possibility suggests that white holes might be relics of the universe's earliest moments. Section 7. The Big Bang, a supermassive white hole. One of the most intriguing theories surrounding white holes is their potential connection to the Big Bang. Some scientists have proposed that the Big Bang itself could be considered a supermassive white hole, an event of immense energy and matter expulsion that marked the beginning of our universe. This idea, while speculative, offers a fascinating perspective on the origins of everything we observe. If the Big Bang were indeed a supermassive white hole, it would explain the sudden emergence of matter and energy that characterized the early universe. The rapid expansion of the universe, observed in cosmological data, could be interpreted as the outward rush of matter and energy from this primordial white hole. This interpretation provides a compelling link between white holes and the universe's earliest moments. The concept of the Big Bang as a white hole also raises intriguing questions about the nature of time and causality. If the Big Bang was a white hole, it would imply that our universe emerged from a pre-existing singularity, a point of infinite density that predated the Big Bang itself. This idea challenges our conventional understanding of time and the beginning of the universe. Section 8. Challenges and obstacles in detection. Despite the theoretical possibility of their existence, detecting white holes presents significant challenges. One major obstacle is their potential instability. White holes, if they exist, might be incredibly short-lived, making them difficult to observe directly. Their brief existence would make them fleeting cosmic events, difficult to capture with current observational techniques. Another challenge is the surrounding cloud of expelled matter that might obscure the core of a white hole. The intense radiation and outflow of material from a white hole could create a dense shroud, making it challenging to observe the core directly. This obscuring effect would further complicate efforts to detect these elusive objects. The lack of a clear observational signature also hinders the search for white holes. While black holes can be detected indirectly through their gravitational effects on surrounding matter, white holes lack a similar readily observable signature. This absence of a clear detection method makes it difficult to pinpoint their location and confirm their existence. Section 9. Implications and future research. The existence of white holes, if confirmed, would have profound implications for our understanding of the universe. It would revolutionize our understanding of space-time, black holes, and the fundamental laws of physics. Their discovery would open up new avenues of research and challenge our current cosmological models. Further research into white holes is crucial to unraveling their mysteries. Theoretical studies combined with advanced observational techniques are necessary to determine whether these enigmatic objects truly exist. Future space telescopes and advanced detection methods might provide the necessary tools to search for the elusive signatures of white holes. The continued exploration of white holes will undoubtedly deepen our understanding of the cosmos and its many wonders. Whether they exist or not, the study of white holes pushes the boundaries of our knowledge and inspires us to continue exploring the vast unknown that surrounds us.